Okay, hey, well, welcome to our first online lab, and we're going to do a dispersion lab. And so grab your lab manual and turn to page 23. And on 23, you'll see the title there, dispersion, and they've got an equation number one. And I want to talk about equation number one and also about your equipment. But to begin with, let me look at a little diagram that we saw actually in class. And so before we had to what's the right word? Social distancing here. We were looking at this diagram here. And so this is what we call the dispersion diagram. And so if you remember, the index of refraction changed slightly with the different wavelengths. And so if you look at this picture, and you can also see it there in your book, this shows a graph of the index of refraction versus the wavelength. And they show some different materials. It's not quite the materials we're going to use today. We're going to use what's called lead glass today. But our graph will look a little bit like this crown glass, and it will have a slightly lower index at the red colors, the wavelength of 700s, and a slightly higher index at the violet colors around 400. And that's hopefully what we will see. Although since we're using lead glass, our graph will be way up here. You'll see we'll get an index way up at about 1.65. And so before we even begin the experiment for today, let me show you another piece from your book. It is this picture here. Let's see, not that one. Right here. And this is example 35.5. And so it couldn't hurt for you to maybe even stop this video for a second and go back and review example 35.5, because your author does a good example of going through here and coming up with this equation. And this equation, 35.9, is actually the same equation as you have on page 23 here, where your author says this is a nice experimental way of finding the index of refraction for a material, and we can look at then the different colors. And so let me just point to the conclusion. Here's the conclusion, n, the index, is equal to, and you got the sine over the sine. The first sine function has two angles in it. The first angle, which is also in the denominator, this phi, this is what we call the apex angle of the triangle. And so up here in this picture, it would be the angle. And for us today, we're going to use an equilateral triangle. In fact, this picture also looks like an equilateral triangle. So I'm just going to tell you that angle is 60 degrees. And so the phi here, capital Phi, is 60 degrees. What we're going to measure here together, and then you can go ahead and record all the data down, is this one right here, the delta. How much did the beam deviate? And let me show you that two ways. I'll start in this picture, but if this prism was not here, this would be the beam of light coming up, and the beam of light would go straight, but because of the prism, it bends going in and then bends again coming out, and so there is an angle of bending, and we call that then the deviation angle. And so that deviation angle is what we need to measure together, because when you put it into this formula, you'll get the index. And we're going to end up doing this for, excuse me, 7 different colors here. Watch, let me turn this off here and go ahead and show you here with our whiteboard optics. Maybe I'll power down the lights in the front, and I'm hoping on the video you can see this red beam going across here, because I'm going to take this equilateral triangle, and this is essentially what I'm going to do here in a second with you, so think of me as your lab partner here, is if I put this in here like that, you'll see that it now deviate. So here's what I mean by that. Let me lower it down and say, okay, this is where the light is currently going. And if I go ahead and put this right here, then this is where the light is going once the prism is put there. Now, there is some adjustments, and you'll see me do this with the equipment. You've got to get the prism adjusted just right so that the light going through the top of the prism is parallel to the base, but that's really easy to do with our equipment. But this right here then is what we call the deviation angle. How much does it deviate? And that's what we're going to be hunting for. What is that deviation angle? And as you'll see here in a second, that angle is slightly different for the different colors or different wavelengths. And that's why then we can then get the index n for the different materials. All right, well, I'll turn the room lights back on here. And let's then zoom in on our equipment right here. And so here's the equipment, and so we're going to perform today's lab, and it's going to function as I'm your partner here. And as your partner, what I'm going to do then is shoot in a bunch of different colors. So let me show you then the equipment. And the big piece of equipment is really right here. I'm going to turn this light source on. And this light source is going to have 7 to 9. We'll just 7. There's 2 of them that are really very difficult to see. So we'll just call this 7 light sources. Probably on the video there, the color looks kind of like a peach color here. And it's really made up of a bunch of different colors. If you're looking in your lab manual and you flip over to page 26, it's step 12, you'll see where the author then lists the different colors and therefore also the different wavelengths that are coming from this light source. Now, you may actually be able to see this a little bit. It's going to be, well, let me explain. The 7 different colors come through here, hits my prism. So here is the equilateral prism, and then they come out at slightly different angles. And so this equipment is a little telescope, and it lets me zoom in on the small angular difference between those two, and that's how we're going to measure them. And so what I'm going to end up doing is look into my telescope here and then move it back and forth, and there's actually a protractor on here which then tells me how much did the angle deviate. And so what I want you to write down is those numbers, and I'll also then show you on a graph here and a table at the end, so in case you didn't hear me, you can write all those down. But I think this will work a little bit because I have a little piece of plastic that acts a lot like this prism, and it'll separate those colors. It's kind of hard to see, but what it'll do is it'll deflect the angle a little bit. And so I'm going to put this right in front of the video camera, and you'll be able to then see these different colors to kind of give you an idea. Now it'll change the angle where the light comes in. So Ron, as you're videoing, I practice with this. If you could shoot the video camera right towards the sink, and I'll turn down the lights, and I'll come back over here so I can put this right in front of the camera. And so here it is. And so those are the images of the light bulb but has separated out the blues and the yellows and the reds and all those good things. Oh, looks like our screen came back on, but I think you guys see it. All right, well, come back over here to the equipment. Let me turn the room lights back on. Let me make this go blank. We're not going to need that for a while. And now let's actually get to the experiment. Let's actually measure them. And so get yourself a pen and or pencil and some paper, and we're just going to write down then what is that deviation angle. And I'll start at the bottom of the chart. The bottom of the chart is red, and the wavelength is, let me just look here, 706.5 nanometers. And so now I'm going to zoom in with my telescope. Now I was playing with this before. Let me move all the way over to the red one. Aha. And you probably can't see the small movement on the video camera here, but I'm just changing this ever so small. And so straight through the light would have gone like this. But now it's hitting this prism and coming through. And this first one then, let me just see if I got my telescope right on the first red one. Okay, good. Is an angle of, and let me just read it here, 50.5 degrees. And so just know that that's the deviation angle for the first red one. Now let's measure the second red one. And so if you're looking at your chart on page 26, you'll see the second red one has a wavelength of 667.8 nanometers. And so let me just kind of move ever so slightly. And so got my telescope right on the red one. Okay. And let me take another reading. And it's 50.8 degrees. And so that's the deviation. And so those two red ones are kind of close together, which, again, hopefully that's what you saw when I put this little piece of plastic in front and turned it. All right, let's go to the next one. The next one is a yellow one. This is a wavelength of 587.6. And so let me turn it just a little bit, right to the yellow. Okay, good. So now I'm zoomed in on the yellow, and I've got 51.4 degrees. Now the next one, which in your book says green and may not be visible, is true. So let's skip that one, the 504.8. Let's just skip over that one because that's so dim I can't record that. So let's go to the next one, which is a kind of a blue-green color, and it has a wavelength of 501.6, as you can see in your table. And let me see if I can get the angle here. Okay, got it. And so for the 501.6, I got the 52.6 degrees. Now the next one isn't much further off. Put my crosshair right there. There we go. Barely moved it. And so I've got 52.8, and that's for the wavelength of 492.2. Let me go to the next one. And the next one is 471.3, yeah, and I got 53.2. And then finally the last of the ones that we're going to be able to see is this violet one, which has a wavelength of 404.9 47.1, and that's in your chart there. And it's at an angle of 53.7. So there's just a small spread there that, again, as you can see, needs this fancy equipment to kind of zoom in and measure that small angle. But hopefully by those numbers you're seeing then that the blues or the violets bent the most and the reds the least. And so there's some kind of hopefully pattern going on here. And so that's your raw data. Now let me say something about your lab manual, because your lab manual, of course, was not built for these new circumstances with an online lab. And so because of that, let me just point out that way back at the beginning of the procedures, step 1 on page 24, steps 1, 2, 3, and 4 are all about adjusting the equipment. And so I did that already. I adjusted the equipment before I even started the video camera. So obviously you don't need to do any of that. I did that, and had we been in class, we would have done it together. I would have said, okay, here's these 1, 2, 3, and 4. And even steps 5 and 6 and 7 and 8 are really about calibrating it and checking it out. In fact, step 8 is asking you to use another light source just to make sure you get the right number. And again, if we were in class, we would do all that together because, again, just reading these small angles and zooming in on the telescope takes some practice here. And so really all of this is saying that you're beginning the lab on the main part of the lab. You don't have to do any of the calibrations or the adjustments or the focusing. And so we're really starting on step 11 here. When that step 11 says use the spectral lines to find the minimum deviation, and then use that equation number 1 to calculate the index. And then they kind of help you through it. And so what I'm really saying is you need to do steps 11 and 12 and 13. Watch, I'll even help show you this because I did some of this already. Let me turn the overhead back on. Let me pull this down. Let me jump over here to graphical analysis. And if I call up graphical analysis, I typed in right here the wavelength. Let me get my pointer. The wavelength that are in the table. And these are the angles that I hopefully just read off to you. And then this third column is a calculated column, which uses that equation 1 I was talking about at the beginning. And so set up that equation. Now, a little bit of warning here. When you start graphical analysis, in fact, let me go back to graphical analysis, because you're obviously not in class here today. You can get to graphical analysis through the virtual desktop. And so you should have gotten an email from our tech director and showing you how to log in. And so just like you would be logging in here, you got to go through their virtual machine to get to graphical analysis. But I'll even say you don't have to use graphical analysis. If you want to use Excel, or if you want to use Google Spreadsheets, or any other program, it doesn't really matter. All we need to do is a curve fit. And so I don't really care which program you use, but I do want to give you one option. And so here's graphical analysis. And so if you choose to use graphical analysis, let me just remind you that when you start graphical analysis, it is in radians. And so make sure the first thing you do, and so I'll come over here and show you, but when you go to your file and you go to settings, you change it to degrees. And of course mine's in degrees because I already set it that way. So I changed it to degrees and I inputted this formula, and so this gives me the index of refraction for these different colors. And so right here was the yellow one, and that yellow one comes out to be about a 165. And then I plotted it here, and so here's the plot. Now as you are doing these, it'll say plot it, and then on step 13 it says do a curve fit, because there was a theoretical physicist, Cauchy, who came up with what we call the Cauchy formula. And so if you look here on step 13, it says that the index should follow this pattern. And I typed it in right here. And if you're using graphical analysis and you do curve fits, and so let me show you the curve fit again. And so under Analyze and Curve Fit, you will notice then that there's a little button here that says define your own function, because there's a lot of ones that are already defined for you. But this one doesn't have a fancy name or anything, so it's not already defined. So you've got to click on this button here, define, and so I typed it in, a plus b over wavelength squared. And so that's what step 13 is. So once you type in that formula, then you can do a curve fit. And this is the grand finale then of the lab, is to show that the index of refraction does change, not by much. You can see that way over here in the reds, we're at, some number just shy of, or, well, shy of 165, but a little bit above 164 right here. And then it goes up to just over 167. And so there's a slight variation through the index of refraction. All right, well, this is our first lab, so I hope it will go well for you. As you can see, all the setup stuff we kind of skipped because I had already done that. But hopefully between seeing this chart and also me saying them verbally, you've got the index. And so go ahead and take those numbers and put them into some kind of program where you can curve fit them in graphical analysis or Google, I guess it's Google Sheets or whatever. And then go ahead and I will say, why don't you email it to me? And that'll be our first lab, and we'll go from there. All right. Bye now.